Okay, you can start.
Okay. So just a quick recap. Last two lectures, what did we do? We sort of stated the PCP theorem, which in more compactly written as NP is in PCP 1/2 order log n order 1. That's what the PCP theorem states. Then we saw its equivalence to inapproximability of max 3 set. It's basically we saw that gap alpha max 3 set star is NP hard. So this said about the hardness of gap max 3 set, how hard is it to approximate. That is, there is some constant up to which you can approximate, and after that you can't. Okay. So what we want to see today is another application to hardness of approximation. Today we will see it's an application towards the hardness of approximating the maximum clique of a graph. So as in the case of max 3 set, it will be good to work with a decision problem. So we want to, given a graph, what's the max clique problem? You have to find the clique of the largest size. Okay, so you can't, we know this is NP hard. So you want to relax our problem and say, let's come up with an alpha approximation. Can we come up with a clique of size 0.9 times the largest clique? That's the approximation problem. Okay, so now if you want to find a clique of this size, but let's talk about this one. You have to output a number which is within 0.9 of the largest clique size. This is what we want to do, and we want to ask how easy or hard is this problem. We'll work with what's called the gap version of this problem. So by now it should
define clique once again.
Pardon?
Could you just define clique once again?
What is clique? Clique is just find a set of vertices. Okay, if you're not working with clique, clique is a set of vertices such that it's a set of vertices. A clique in a graph is just a set of vertices so that every two vertices in that set are connected by an edge. It's a complete graph. Clique is a complete graph. Yeah. So we'll talk about gap clique. Gap alpha clique. It's the promise problem which is defined as follows. The S instance is a graph G and a number K such that there exists a clique of size larger than or equal to K in G. And no, the NP complete case, no will also be instances of the form G comma K. The usual every clique is of size smaller than alpha, than K. Instead of saying smaller than K, we'll say smaller by a constant factor. Every clique in G is of size smaller than alpha. The alpha is some number in 0. if you understand the hardness of this problem, we will know how well can we approximate clique. So the goal for today's lecture is to ask, does there exist an alpha in 0, 1 such that there is a polytime reduction from SAT to gap alpha clique? Because if there exists such a reduction, then it will say you cannot approximate clique to a factor better than alpha. From what we had done, the same sort of thing should. And by the way, so for max 3 SAT, we saw a 7/8 approximation. For clique, what's an approximation you can give among algorithms and among the efficient algorithms?
For something.
Coloring, right?
What?
So you want to find.
I want to just find the size of the largest clique. I know it's hard to find this, so I want you to give me a number instead, which is guaranteed to be within a certain factor of the size of the largest clique. And what is this best guarantee you can give me? Okay, what's the weakest guarantee sort of you can give me? So I can output one vertex. That's certainly a clique. It's within a factor 1/n of the size of the largest clique. That's one thing to do. Okay, you can output two vertices. If you can take an edge, if the graph has an edge, you can output two vertices.
There are m edges, you can do m vertices.
How?
If there are m edges, you can do like m vertices or n/2 vertices, something like that.
How can you?
For every edge, I'll just pick up the vertex.
Yeah, but that's not a clique. You have to give me a clique that approximates. You have to, given a graph, this one, you have to guarantee to me there's a clique of size. You have to give me a clique of size at least so much. What's the guarantee? What's the best approximation? I claim you can get a 1/n approximation guarantee trivially. That should be trivial because you just output a vertex. Satyajit, I do not know if you're. So what's a clique? Once again, let's go back. A clique is a set of vertices so that every pair of vertices within that set are connected by an edge.
Okay, yeah. If you pick up these m vertices, then it can't be the case because you could have two vertices which are not adjacent.
Yeah, which are not adjacent. So, but I want for example, for max 3 SAT, we gave a 7/8 approximation algorithm. For vertex cover, we gave a half approximation algorithm by doing something. So vertex cover was a little clever. It used a maximal matching and did something. Max SAT was not that clever, but because it completely ignored the formula. It just picked a random assignment, but you needed something. You needed to conditional expectations, or you needed to some linearity of expectation to show that even a random one satisfies a 7/8 probability. Clique, I'm going to do something even more stupid. I'm going to just say output one vertex. That's certainly a 1/n approximation to the size of the largest clique. And what we'll show, we won't be able to finish the whole thing today. We'll show fair parts of it. We'll show that this is basically the best you can do. If you can do anything better than this, you might as well be, you will be showing NP equals P. That's the current state of affairs, but we will build the theory today, assuming the PCP theorem will be built towards this result. Okay. So what we will show, the main theorem we will show today is the following theorem due to Fege, Lavash. Keep missing Goldwasser always. We do not know why. Goldwasser, Lovas, Safra, and Segedi from 91, which states the following. That is, if L is in PCP C, S, randomness equals R, query complexity equals Q, and time verifier is T, then there exists a deterministic reduction, deterministic order T times 2 to the R plus Q time reduction from L to gap C by S, should be S by C, S by C, S by C, clique. So let's stare at this for a while and see what it is stating. This is what we will spend a fair part of the lecture proving this theorem. But let's state what it is. Let's stare at what the theorem is. Okay. So suppose I manage to show a PCP for a particular language. Yeah. What is the stating? I show a PCP for a particular language, and I show that the PCP has some properties. You use only R random points, Q queries, the PCP making Q queries to the proof, and the running time of the verifier is time T. Then I will use this reduction, this fact that there exists such a restricted verifier with this property, to actually construct a reduction from L to gap S by C clique. And furthermore, the reduction will run in time T times 2 power R plus Q. Okay. So even before we go into how do you prove this, let's recall the PCP theorem had stated that SAT is in PCP 1/2 some C times log n plus say some constant Q. This is what the PCP theorem had stated. Now what does PCP theorem plus the FGLSS theorem, if you put them two together, what does it say? There exists a
deterministic time reduction to
running in time. How much?
What was T in SAT?
T in SAT is polynomial. If I don't mention it, it's polynomial.
Okay, so it's like 2 log some poly n.
Yeah, so there exists a P time reduction, a poly time reduction from SAT to gap half clique. Just putting these two together, you get this. Is that clear? So this already will tell us, that is, if you assume the PCP theorem and this theorem which we will prove at this one, that is half approximating the clique is NP hard. The max clique. Is NP hard. I said even 1 by n approximating or little more than 1 by n is NP hard. We'll come to that later, but right now this is all we have, and we will see how to prove this. Is this clear?
Yeah, something tangential. So what is the best that we know for coloring? Does this also tell us something about?
No. So coloring is a different beast. Coloring we do not have. So coloring, regular graph coloring, what we do know.
Prahladh, your
is,
screen share stopped.
What's happening? 1 second. So coloring is a different thing. You want to. So by the way, just before when that you ask coloring, clique and independent set are the same. This one, because clique independent set is just doing clique on the complement graph. So whatever you get for clique, you also get for independent set, and it's conceivable that FGLSS wrote it in terms of independent set or not clique. I do not know what they wrote, but this is the same thing. Coloring is a different problem. Coloring is you want to partition the graph into as few independent sets as possible. That's the coloring problem. So the best algorithms for coloring. So we know it's already NP hard to 3-color a graph. To check if a graph is 3-colorable, even to check if a graph is 2-colorable, this is easy. This is just checking bipartiteness. Now to check if a graph is 3-colorable, this happens to be NP hard. So now you can ask several things. You can ask, there are a few questions. You want to come up with the best approximation to the chromatic number of the graph. This is one. So in coloring, there are 2 questions you can ask. I want the best approximation to the chromatic number. Or given a graph that is 3-colorable, what is the smallest number of colors you can efficiently color it such that every color class is an independent set? These are 2 questions which you could ask. In the first question, I don't tell you what's the chromatic number, but you want to approximate the chromatic number. Second question, I tell you the chromatic number is 3, except I haven't told you what is the 3 coloring, and I want you to find out a valid coloring, but efficiently. Of course, if you drop the word efficiently, you just go over every possible 3 partition of the graph and find out if one of them is a valid 3 coloring. So these are, so the notion of approximation, you can ask both these questions. You can ask the first one, you can ask the second one. Both of these are potential questions you can ask. The first one we understand well enough, and basically we can show the chromatic number also requires close to factors of n. You can't approximate it to any factor less than n, something around n, or at least polynomial in n, like square root n or some such thing. The other question is a big open problem. We don't know how to solve it. So the current best algorithms, given a 3-colorable graph, we can color it with n to the power 0.2 colors. That's polynomially many colors, even though I know that the graph is 3-colorable. By the way, this is not a laughing matter. Wigderson's thesis was in which, so a 3-colorable graph, you can certainly color it with n colors. This is trivial. Any graph you can color it with n color. Why care if it's 3-colorable? Wigderson in his thesis showed that a 3-colorable graph can be colored with square root n colors. You can do it in square root n. And this n to square root n. N is trivial. Square root n itself was this one. It's an easy algorithm. It's an algorithm which I can describe to you in 10 minutes or 10, 15 minutes. An easy algorithm. This was Wigderson's thesis. And since then, that n to the power 0.5 over, this happened in the 80s, in the early 80s, I believe, Wigderson's thesis. Since then to 2000, we are in 2010 now, 2021, sorry. So it's 40 years, and we have moved from, the exponent has moved from n to the 0.5 to n to the 0.2. We know how to color a 3-colorable graph to say n to the 1.99, n to the 0.199999 colors. But hardness wise, unfortunately, this is all that we know is it's NP hard to color it with 6 colors or 7 colors. The gap between these two, unlike max 3 sat or max clique, which we really, the upper and the lower bounds really meet. We know easiness up to a particular point, and just beyond that, we know the problem becomes hard. Coloring is a thing in which it is open for graphs, and this has to do, I'll spend some time on why, in the end of this lecture, if I have time, I'll spend on why coloring and some of these problems fail to sort of grasp this. If once we move to hypergraph coloring, we know something to do a little better than this. That is, if you allow the graph to have the edges to have 3 vertices per edge rather than 2, then we can do something. And I'll talk about this later on in the lecture if I have time, if I finish the FGLSS reduction. So people follow the, so let's just go back to the statement. This is a statement we want to prove. Statement we want to prove. And let's see if we understand this and if we can. I want to prove this statement. Okay, so let's, so proof. The FGLSS theorem. And so what do we need to give? We need to give a reduction. We need to give a reduction. And the funny thing about FGLSS is they didn't have to give a reduction. They actually used a reduction, off-the-shelf reduction. They just had to observe that this off-the-shelf reduction had this property. But it was a very crucial observation. It sort of changed the world of study, the understanding of our hardness of approximation problems. They, in fact, their reduction in some sense is, of course, when they did it, the notion of PCP itself was not defined. So it's unfair to say was just this, but the reduction is just the usual carp reduction from SAT to max clique. But we'll see what I mean by that. I will expound on the statement in the remaining minute. It is exactly this, but in using starting from this one. So let's once again, we have, what are we given? We are given L is a language in PCP, C, S, R, Q, T. And what we want a reduction R that maps L to gap C, gap SC. S by C clique. So given any instance of the language, I need to construct a graph Gx and a number Kx such that if this were if X is an S instance of the language, if X is in the language, then G, K is an S instance of gap S by C clique. If X is a no instance, if X is not in the language, then Gx, Kx is a no instance of the gap problem. This is what we need to do. So I need to construct this graph. So give me an instance X. Give me an instance X of the original problem of the language L. From that, I need to construct an instance of the gap clique problem. Which is, what's an instance of the gap clique problem? It's a pair. It's a pair. I had to give the graph Gx. I had to construct the graph Gx from X as well as a number Kx associated with the graph. And this, it should be an S and no instance depending on whether X is in the language or X is not in the language. Okay. And how are we going to do this? So what do we know? We know L has a what do we call RQ. I'm going to drop the other parameters, RQT restricted verifier. Once again, what does this mean? This means on input X, the verifier tosses at most R random coins, decides to probe the proof at just Q locations, and then accept and comes up with a predicate, but does all of this within time T. And then if the string is in the language, there is one such proof which causes the verifier to accept with probability C. So C fraction of the random tosses will cause it to accept. If X is not in the language, then no matter which proof you give me, at most S fraction of the random coin tosses will cause the verifier to accept. Okay. So this is all that we have. We have L has a restricted verifier which has this completeness and soundness property. So let's write that down. In the completeness case, we have that X is in L implies there exists a proof pi such that probability over the random coins of the verifier. So it gets to see X, it gets to see the random coins, but it gets to only query the proof pi. That's why I'm going to put pi in this one. This is equal to accept is greater than or equal to C. And soundness says that if X is not in the language, then no matter which proof I feed this verifier, the probability that V pi X comma R equals accept is less than S. And we need to come up using this. All that we know is this, that the verifier, that L has such a restricted verifier with this property. From the belly of this L, from the belly of this verifier, I need to pull out the graph G. Okay. So
what is KX? Is it just K?
It is just.
Why
I haven't yet defined what GX is, what KX is. I'll have to show you what both the reduction. KX is a number. KX is a number.
But KX should depend on X.
It will depend on X.
Okay, then I don't follow the thing. What is, you want to send a yes instances to instances which have large cliques and no to instances which have small cliques, and there is a gap between these two.
Yes.
So then if you let me do it per X basis, what is left?
No. So recall the gap is coming in the definition of the clique. So it's a gap alpha clique. So in the S case, there is a clique of size at least K. And in the no case, every clique of size at most alpha K. So the alpha is, it's a fixed alpha for the whole gap clique language, the promise problem. And then I'm allowed to vary K for every input.
Okay, sir. Yeah.
Okay. So the approximation factor is not coming from K, it's coming from alpha. So it's coming from over here, this guy. Okay. So this one over here for us. How are we going to do this? So I'm going to construct this. So let's fix an X. So X is an instance of the language. It could be an S instance. It could be a no instance. So this is exactly what I'm going to do is going to be exactly the carp reduction, but stated in this language, stated in the language of this one. So what is it? So I'm going to, let's first construct GX. I'll then tell what KX is. GX is we are going to construct a multipartite graph. It will eventually be a multipartite graph. It will be a multipartite graph. And what will be the parts of this graph? Each part will correspond to a possible set of random coins the verifier can toss. So they will be the vertex set of this graph.
Did we do this reduction back in during the previous lectures or no?
No, we didn't do this. In some sense, we did it when in the second lecture of the course when we did NP reduction from SAT to clique. It's
every partition has 7 vertices or something.
There we did every partition has 7 vertices. So what was that? There we had let's recall that. What was it? We had given a SAT. How did we come up with a clique? We came up with a partition for each clause, and each vertex had each thing had a 7 vertices which correspond to the 7 satisfying assignments of that particular clause, and we put an edge between 2 vertices if they were consistent with each other. So within a part there won't be any edges because they are all inconsistent assignments. Across edges, if they didn't share a variable, you would put an edge because they are obviously consistent. If they shared a variable, they should both be saying the same things about the variables. That was what, and we're going to do exactly the same thing. We're going to do, that's why I call this a carp. It's the same carp reduction. Instead of the number of clauses, the clauses are going to be replaced by every possible random coin. So that's why we have, this is R1, R2, and eventually R2 par R. There are, so that for every random coin, we have a part, and we are going to have, there we had 7, because 7 were the possible satisfying answers. What we'll put is we'll put all possible answers. We'll put 0, 1 to the cube. That is every possible query that you can see on these Q locations. Every possible answer that you could see, that's a possible vertex. So everything corresponds to a possible local view of this one. This is, so unlike 7 over there, we're going to actually put 8. We're going to put all 8 vertices, all the 8 possible things. Now I need to define to you. So is the vertex set clear? That's the vertices. It's just this 2 per r into 2 per q sized vertex set. I have to now, of course, I haven't put any edges there. I'm going to put the edges, which are basically going to be consistent. It's going to be the consistency graph. So I'm going to define EX.
Prahladh, can you please reveal what's inside each of these parts?
Each part refers, so the number of parts is, there's a part corresponding to every random coin. Therefore, there are 2 per r parts. And for each part, you're going to say every possible things that you could have seen, the verifier could have seen. The verifier is querying q locations now based on the random. Now, once you fix the random coin, it's going to look at q locations. What are the things it could see? It could see 2 per q possible views. And for every possible view of the verifier, I'm going to put a vertex. It's exactly like in the case of the SAT, which Satyajit said, you put 7 vertices or 8 vertices for every possible local view for that clause. That clause involves 3 variables. For every possible assignment to the 3 variables, you put a vertex.
Here the clause is equal to the random coins, and the
clause,
number of vertices is equal to the q places you are looking at.
Places you're looking at, yes. So I'm going to tell you when is R1 and then a B11, B21, B1, Q. When is this adjacent to R2, B21?
Prahladh, do the queries being adaptive or non-adaptive matter here?
So for this construction, I think the queries could be non-adaptive. This could be non-adaptive. This could be adaptive also. This could be an adaptive PCP.
What does it mean by adaptive?
So after you query the first guy, the second guy you pick based on the second location, which is a, so the verifier tosses R points and decides Q location. That's what I said. That's a non-adaptive PCP. It decides which Q or locations it's going to probe upfront. It could decide this is the first location I'm going to probe. It probes it. Based on the answer, it decides which is the second location it's going to probe. And then based on that answer, it's going to decide which is the third location to probe. That's an adaptive verifier. The proof which I give will work even for adaptive verifiers. Except that these answers will not be the 2 power possible. It's a 2 per q possible local views. Okay. Can I write this for adaptive? 1 second. I think I can write it for adaptive. Okay. So when will I put an edge? If the following 2 conditions are met. One, B1, B2, the first Q queries and the second Q queries should both be satisfying assignments for that particular random point. That is for both I in 1, 2, this BI bar is a satisfying assignment to the predicate for on random to the predicate DRI, the predicate, the verifier constructed a predicate based on randomness RI. So if you go back to the clause, the SAT example, if both of these should be both the 3 bits, here, you put an edge only if they are satisfying assignments. The first condition has to check if they are not, if the 3 bits are a violating assignment, that's an isolated vertex. There cannot be any edge getting out. That's the first condition. And the second condition is the 2 things are consistent with each other. The two local views.
What does consistent mean?
I'm writing it informally. What does consistency mean? Consistency means the following. Now, on a particular random point, let's look at, you're querying let me write it for simplicity for the adaptive setting, but this can also work for the say it for the non-adaptive setting. It can also refer to the adaptive setting. On particular random point, suppose you're going to query the locations 3, 10, and 29 over here. And over here, you're going to query 10, 15, and 38. And here you're going to query 29, 38, and 99. These are the locations. So I have 3 bits over here. I have 3 bits over here. I have 3 bits over here. So notice firstly, so what I want to say is I'm asking when am I going to put an edge between this and this, this and this. These are what I'm asking right now. Now, this vertex here refers to, so suppose this vertex here was 0, 0, 0, and this was 0, 1, 0, 0, 1, yeah, 0, 1, 0. I will put an edge between 2 vertices. They are now referring to certain proof locations and an assignment to those proof locations. They should be consistent on the intersection. This is just like the same case as in clauses. This is talking about 3 variables. This is talking about 3 variables. And if they are talking about any variables, if there's a any variable in the intersection, both the assignments should give you the same value for both the assignments. Both the vertices should give you the same assignment. That's what consistency means. Is that clear? It's the same definition of consistency as before.
No, this isn't clear.
So what is each vertex referring to? Each vertex is referring to a particular set of Q locations that the verifier is probing and a possible assignment to those Q locations. Each vertex is referring to that. It's a particular set of Q locations and a possible assignment to those Q locations. Now, another vertex is referring to a different set of Q locations and a possible assignment to those Q locations. If there was any intersection between the 2 Q locations, then they should be referring to the same assignment among the intersection. That's all consistency means. So for instance, this guy is referring to the 10th location. This guy also is referring to the 10th location. So the 10th location is getting 0 here. The 10th location is getting 0 here. And that's the only intersection. Therefore, there will be an edge between these 2.
If it was a 1 and a 0, then it wouldn't have been the case.
It wouldn't have been an edge. For instance, by this definition, there won't be an edge between any guys over here. Over here, there will be no edges because everything here, these are all referring to the same set of locations if it is a non-adaptive PCP, and they are all inconsistent with each other. Even in an adaptive PCP, these will all be inconsistent with each other, but let's refer that. But this is going to be this is exactly what happened in the class case, in the usual car production from SAT to clique. Okay. That's going to be the graph. That's the entire graph. It's sort of the consistency graph corresponding to the PCP. So so the graph is this. And what is Kx? Kx is, I'm going to output, is going to be C times 2 power R. We will shortly see why. So I have defined the graph to you. I defined Kx to you. So that's the instance. So X has been mapped to the instance Gx, Kx. I'll have to show the completeness and soundness, but before that, let's just check the whole thing is efficient. Or what's the running time of the reduction?
To the Q plus R.
2 to the Q plus R, no, and times T, because each time it has to run the verifier. So it's exactly 2 to the Q plus R times. That's why the verifier runs in. Plus some chiller possibility to do these counts and all, but I'm going to ignore all of that. It has to maintain a counter that it's going over all randomness, but let's ignore that.
So why is it a T in there?
Because it has to run, based on the random coins, it has to find out which are the Q locations and whether it's going to accept or not. So it has to decide, it has to do all of this. So for every random coin tosses, it has to find out which are the Q locations it's going to probe and what is the accepting predicate for them.
Yeah.
Okay. This is almost like the seventh thing in the case of the car production, which we did in NP completeness, we put only 7 guys. It's almost the same thing. Here also, we are putting only the satisfying assignment because all the violated things are isolated vertices over here. If you recall, there are no edges going out of them. So there's the same thing as that. They will not change the clique size because they are isolated vertices. So even in that case, you could have put 8 vertices for each part, and for the one unsatisfied thing in each part, we just make it an isolated vertex. That will not change the clique size at all. Okay. Now, what do we need to show? We'll have to prove the completeness and soundness. So let's start with the easier thing, completeness. Suppose X is in the language. That means probability over the random coins. That means there exists a proof pi. So that probability over the random choices V pi X comma R equals accept is greater than or equal to C. Now from this, I need to show that there is an independent set of large enough size. A clique of large enough size. Notice that any clique can pick up only one vertex from each part because there's a multipartite graph. There are no 2 vertices in a part there are no edges. Each part is an independent set. So it can only pick. So what is the clique? It should be very clear that this is the guy I'm supposed to pick. Yes, pi is just going to be those R comma B bar pars. Such that firstly R is in 0, 1 to the R. It's a randomness. Q and D are the thing produced by the verifier on this particular input and randomness. D of this B bar is accept, and pi when restricted to this Q is exactly B. So it's exactly that part. You're going back to this graph. There is pi. So pi is a assignment to all the possible locations. Pi is a proof. So there is one vertex here which corresponds to exactly agrees with pi. There's another vertex here which agrees with pi. There's another vertex here which agrees with pi. So what I'm doing is just picking up those set of things which exactly agree with pi.
Could you just go down as to what you have written?
So what are the vertices I'm going to pick up? So given a proof pi, I'm going to pick up, given a proof pi, what are the vertices I'll pick up? I'm going to pick up all those vertices which are consistent with this pi and contribute to a satisfying predicate. So let's go back. See, you have a proof pi. A proof pi is an assignment to all the variables, all the locations. That's what a proof is a setting. So there is exactly one guy over here which is consistent with pi. Similarly, there is one guy over here that is consistent with pi. There's one guy over here that is consistent with pi. These are all the things that are consistent with each other. Now, furthermore, among them, I'm going to take pi satisfies certain random coins. Possibly this random coin, when you run it, this one satisfies. This random coin satisfies. This one possibly it does not. So I will pick only those vertices which are among the satisfied random coins. That's what I mean over here. So firstly, this means by pi, this is the picking a vertex if the local view, if the B bar is consistent with pi, and furthermore, the view should be an accepting view. Okay. That's this one. Now I want to say by definition, the way I have defined it, yes, pi is a clique. Every pair of vertices in S pi, firstly, they are all accepting views. That's how I defined it. They are all accepting this. So they all satisfy condition 1. And they are consistent with each other because they are coming from a single global assignment. Therefore, there is between every pair of them, there is an edge. There is no inconsistency between them. So S pi is a clique. Satyajit, are you okay? Same bit. Okay. So S pi is a clique. And furthermore, what more do we know? What is the size of S pi? SPy is picking exactly one vertex from each part, at most one vertex from each part. But you know the number of parts it's going to pick up is it's going to pick up at least C fraction of them is going to have a vertex. So it's SPy is going to be certainly larger than C times 2 power R.
So just one thing. So if you have R random bits and then you get a B, so every R has 2 raised to Q B's, such B's.
Yes.
Then so you are just picking the B which when
it's consistent with this proof.
Q, which when restricted to Q is like B when pi is restricted to Q, it should be equal to B.
Yes, I'm only picking that B.
And this B should also satisfy what?
Yes, it should satisfy the predicate, whatever predicate the verifier is testing. So like in the clause case, it should be a satisfying assignment to the predicate. Those 3 bits should be a satisfying assignment to the predicate.
Now this is a why was this a clique?
Why is this a clique? Let's look at all the vertices that you pick up so far. For it, I want to say that any pair of them have an edge between them. Why is that true? Take any two vertices in this set that I have picked up. It clearly satisfies condition 1 because by definition B is happened to be a satisfying assignment. So condition 1 is satisfied. Both the endpoints are satisfying the corresponding randomness they satisfy. Now they ask is, are they consistent with each other? They are both coming from the same local global proof. Therefore, they are obviously consistent. They can't be inconsistent. They are both restrictions of the same global object. Therefore, they are consistent. Therefore, between every pair of such vertices in this set SPy that I have defined, there is an edge between them.
Yeah. Okay.
Therefore, SPy is a clique. And furthermore, how large is SPy? SPy is at least C times 2 power R because of the completeness property. So that implies that Gx, Kx in this case is in the yes part. So this completes the completeness proof of.
Every R has at least C, guys, and there are 2 raised to R.
No. There are at least C fraction of the R's satisfy have the C fraction of the R's will be this one. Therefore, every R has only one guy, and there are C fraction of them. So the number of R's is 2 power R. Therefore, you get C to 2 power R.
Yeah, it's a fraction. Yeah.
Okay. And if you follow this, soundness should be exactly this one. Soundness, what do we want to show? Let's prove the contrapositive. Let's suppose Gx, Kx is not in no. That is the size of, that is, there exists a clique. There exists a clique of size. Let's call the clique. There exists a clique S of size.
K. At least alpha K.
And what is alpha? Of alpha times Kx, which is what is alpha? Alpha is S by C. And this was C into 2 power R. Therefore, there's a clique of size at least S times 2 power R. So there is a clique of size at least S times 2 power R. So now let's go back to this graph. Let's call this clique. This is a clique. Let's go back to this graph. Let me draw the graph again.
So if it belongs to no, then it is at most S times 2 power R.
No, but 1 second, wait. Let's before that going that. So this clique is picking up. Say it's picking up. These are the vertices. These are the clique. Firstly, I want to show that this clique cannot pick up more than one vertex from each part. It's a clique. So it can't. Each part is an independent set. Therefore, it can pick only one vertex from each part. So it's a clique like this. It picks up. Suppose these were the parts it picked up, and the other parts it didn't pick up. Now look at these locations. You know that these are all consistent with each other. That's the definition of clique. That's the reason why the edges exist. So I want to say, looking at this, I can build a global proof. That is, you can construct a proof. We can construct a proof. So given S, clique, we can construct a proof pi such that S is actually equal to S pi, or S is a subset of S pi. Are people with me in this? Because they are consistent with each other, so I can globally I can give this assignment, and therefore if it doesn't talk about some variables, I could just extend them arbitrarily. But then this will imply that this proof, then this proof pi satisfies at least S fraction of the random, because of the random coin tosses, which implies that X is not in L. Because if X is in L, which implies what does it imply? It implies that X is in L. Because if X is not in L, it can satisfy strictly less than S clauses, S fraction. Therefore, this is violated. Therefore, X has to be in L. Therefore, you get the contrapositive. Hence,
when X belongs to L, how many were, what was the size of S?
No. If X belongs to L, we got C. Right now, let's look at this one. What I have said, what have we got? We have managed to get a proof for which we have got a proof such that this is violated. I found you there exists a proof for which this is greater than or equal to yes. If that is the case, it can't be that X is not in L.
Yeah.
Therefore, X has to be in L.
Yeah.
That is, X is not in L implies Gx, Kx is in no. This is the contrapositive. We proved the Gx, Kx is not in no implies X is in L. Therefore, the contrapositive, and hence the soundness is there. Are we good so far? This is exactly the same reduction as before. Observing this is just exactly the original car production. Proving NP completeness.
So Kx is always C times 2 power R.
Kx is always C times 2 power R. And if it's perfect completeness, it's always 2 power R because C is 1.
Okay.
Yeah.
So we actually can get the reduction is stronger. It just, for a particular K, it just gives you either we are above this clique size or well below.
No, but the K is changing and depending on the input length, no? So if you fix the input length, 2 power R is a number changing based on the input length.
On the number of coin tosses you.
Yeah. So it is dependent on the input length, but oblivious of what the actual assignment. Once you fix X, it is determined. Once you fix the length of X, it's determined. It doesn't depend anymore on what X is.
Yes.
And it's this all that if the FGLSS is doing is it's realizing that this reduction is in what is called an approximation preserving reduction. I won't define this, but essentially this proof above is showing this fact. That is, if you had a gap, like PCPs had a gap, they have a gap between C and S in one world, the reduction also maintains the gap. though the original reduction was only defined between languages to languages, this is actually also a reduction between gap problems to gap problems and maintains the gap. That's all that is happening over here. Okay. So is this reduction clear? It's the same reduction as we did viewed in the, once we have a PCP statement, we have a gap problem. We are viewing it from the lens of the PCP theorem. That's all. Okay. So what did we what did we have? We had, so let's putting everything together. This we did it at the beginning, but I want to do it again. Putting everything together. So the PCP theorem gave us that SAT is in PCP 1/2 order log n and possibly 3. So let's make that also fix. Say C log n 3 for some fixed constant, for some constant C greater than or equal to 1. That's what the PCP theorem said. The FGLSS theorem says L is in PCP C, S, RQT implies there's a reduction from this to gap S by C clique in time order T times 2R plus Q. You put this together, you get the following corollary. You get that in NP hard to approximate clique to a factor better than half. Okay. Is this fine? People with me so far? Now, suppose I want to make this half to be, I want to say why half, I want to say even 1/3 is hard or 1/10 is hard. That's a better and better result. What does this depend on? This. So if I wanted to improve this half to something, that only depended on this number, this ratio between these two. That's what determined this guy. This is this guy. I want to get this. Half came from S by C. S by C was half over 1 year. If I make that number between completeness and soundness to be even, the ratio of them to be even smaller, then I get even better and better gaps. But this, just notice, so I want to improve this gap between these two. So it's a PCP is a randomized algorithm. You repeat it twice, the whole algorithm twice. In the yes case, it's perfectly complete. The same proof will work, will give you PCP 1, the completeness 1. So all I want to claim is the following. Just do sequential repetition of, let's just do if you repeat a PCP twice, if you repeat the verifier twice, if you repeat verifier twice, you will get that PCP 1, S, R, Q, T is basically contained in PCP 1, S square. The soundness will fall if you accept, if only both of them accept, and R gets replaced by 2R, queries get replaced by 2Q, time gets replaced by 2T. So in general, you could do this. You could do K sequential repetition. And you could get PCP 1S RQT to be a subset of PCP 1 S to the power K, KR, KQ, KT. Are people with me this? I'm just repeating the restricted verifier K times. I'm just running it K times, and I'll accept only if all the K runs accept. So it's going to toss k number of points. It's going to possibly query k times as many queries, and its running time is k times larger. But what is the advantage we get? The soundness falls by a factor of s to the k. That is, in the s case, of course, if there is a proof that satisfies with probability 1, it will still satisfy with probability 1. But in the no case, if this proof satisfies yes, the probability of how, if every proof violates with probability yes, then the possibility the proof will satisfy all the k things will be at most s to the power k.
So if you in the first repeat verify twice, you got a PCP 1s square. If you repeat the 1s square once again, then you'll get 1
s power 4r 4 cube.
The rounds will increase.
Yeah, it's a sequence. That's why if you repeat it k times, you get this.
Yeah.
Notice, why am I doing this? Because it was this ratio that mattered for, this was the ratio, and I want to make this ratio as small as possible. So starting from half, I can make it half to the power k as much as I can. But notice this comes at the cost, the running time increases. So let's think of any constant k now. Any constant k, this will become half to the k becomes 1 over 2 to the k. So for any, so in particular, we have that SAT is in PCP 1 by 2 to the power k, kc log n, 3k, and some, this is once again poly. Now let's do this repetition. Now apply the FGLSS theorem to this. Now I have SAT is in this object. So I get a better gap.
1 over 2 to the k.
1 over 2 to the k. Therefore, a corollary of this will be that, and k is at our choice. We could have chosen k to be anything. Anything subject to what? Subject to the fact that 2 power q plus r is still a polynomial. Once that goes beyond polynomial, this will no longer remain a polynomial time reduction. And for q power r to be a polynomial, k can only be a constant. Because once k becomes super constant, 2 power r will become super polynomial.
Then it will be like 2 power n something.
Yeah, but no, it will become super polynomial, not 2 power n yet. For that, k has to go much larger. So at the end of this, what we'll get for any constant k, you can get this. So all I'm claiming is for all constant alpha,
Gap, max clique,
gap alpha, max clique
is NP.
is NP hard. So it's not just half hard, it is 1 by 10th hard, 1 by 100th hard, 1 by 1000th hard. Any constant you give me, you cannot come up with a clique which is of size within this factor of this one. This is still not what we wanted to prove. What we wanted to say, our best approximation result which we had was a 1 by n approximation. This is still this is a fixed constant. Now let's ask if you can push it further to get 1 by n from this. So is this theorem? So these are the sort of theorems which we have proven. This is putting this together.
Prahladh, do you want to say that this part below is just tensoring the original graph? I mean, we could have done it without the PCP boost.
You're not going to take away a potential problem from a problem set by asking this question, okay?
The thing about Prahladh is every time he tries to do something in the problem set, the question comes up in the lectures itself.
Yeah. Okay. So this is this. Now I want to make k to be even small. I want to increase k to even larger. Right now, the reason we could do this was k was being made to every constant. I want to make k super constant now. What is preventing you from becoming k to be super constant? This it's multiplying the randomness. But there is a question. So you can do the sequential repetition. So this will be an aside for those of you who have done my other or who are taking the other course, the toolkit course. We saw how to do this. The sequential repetition using not you. So why did we get k times log n? We picked the k random points independently, not using independent random points. This is k times c log n. That's why we got this. But using a k-step walk on an expander on a spectral expander. So you don't need to know what these objects are, but you can spectral expander of size 2 power r. If you do it on that, the randomness needed is not so much, it is c log n plus order k. You can get the same error reduction, not with the multiplication of k, but with the additive k factor, and not with the multiplication. This is something you can do with sequential, in which you don't pick up the coins independently, but you pick up the coins in some correlated fashion by walking on an expander. There is this process. This will tell you that PCP 1S RQ.
You have the k to be log n.
Huh?
You can have the k to be now, you can have it to be log n.
Yeah, that's precisely. You can now make it PCP 1 by 2 power k. Sorry, 1 by 2 power k. So let's write this as just half for. This will be r plus order k. This will be order kq. And this will be order k. So now k can go as large as log n, exactly as Satyajit pointed. Previously k was restricted to be only constant. Now you can push k to be, now we can make k as large as any theta log n. And then you put all of this together, you will get the following corollary of this. You will get that there exists a delta in 0, 1 such that gap 1 by n to the delta clique is NP hard. So this delta will be like 0.1 or 0.01 or something. So it says even approximating clique within a factor 1 by n to the 0.1 or 1 by n to the 0.01, that is hard to get. You can't do this. Just sequential repetition will give you this object. Okay. So this is sort of, so this is what is called, recycling randomness. And you could ask, why does this stop at only n to the delta? Why doesn't it go all the way to 1 over n? The reason being, the size of the graph is 2 power q plus 2 power r. The size of the graph is 2 power q plus 2 power r. The size of the largest clique you are getting is only 2 power r. Therefore, the clique size compared to the graph is off by a factor 2 power q. And 2 power q has now become itself a polynomial. Previously, 2 power q was not a polynomial because k has become log n at this case. 2 power q is a polynomial. So you're always off by a polynomial factor, and that polynomial factor is this n to the 1 minus delta. It's because the queries are also increasing. The queries are also increasing along with you doing this repetition. So then there was a subsequent result due to Hardness, who showed that you can, just like you reduce the queries, you can also, just like you reduce the randomness using recycling, you can also sort of recycle the queries. And I won't tell you how to do this. You can recycle the queries and you can prove that gap 1 by n to the 1 for all epsilon in 0, 1, gap 1 by clique is NP hard. You can show this. That is, you can make that 1 by n to the delta, you can push it all the way to 1.
This is a much stronger than the result than the corollary, right?
Yeah, this is a much stronger.
The delta in the above.
The delta in the above will be some, I think you get half. If you do the best of worlds, you will get half. Q and R, you can balance it to get half, but you can't get better than half. This one says the half can be pushed in the exponent, you can push it all the way to 1. Except Hasta's original reduction was NP hard under randomized reductions. He could not give a fully deterministic reduction. And then Zuckerman reproved the same result and gave it under deterministic reductions. And that basically says our trivial algorithm of trying to get outputting one vertex is as good as we can do. If we can do anything better than that, we will be proving NP equals. We'll be giving a polynomial time algorithm for SAT. Okay. This is recycling queries. And NP hard. And basically, what was being understood over here was this following one. I have about 10 minutes more, so I'll just spend some general prospect. What was done over here is, what did we do? That is, each time you paid an extra query, you did an extra query. Question is, how much does the soundness fall by? So Hasta in his proof basically tries to analyze this quantity called amortized query complexity. That is, what does each additional query by you in soundness? So for instance, over here, if you look at this result, each time you make an extra 3 queries, the soundness falls by a factor half. So every 3 queries, the soundness falls by a factor half. This is what we showed over here.
Oh, where did we?
Here, you make 3 more queries, the soundness falls by a factor 1 by 2. So every three queries, the soundness is falling by a factor half. What Hasta wanted to understand is, do you need 3 queries for the soundness to fall by half? What he said is, initially, possibly you need 3 queries to get to half, but as you make K larger and larger, every additional query will reduce the soundness by a factor half. What he actually showed was each additional query in the limit, and this is what amortized query reduces soundness by half in the limit. And that's exactly what he wanted to. That's how he proved the clique result was proven by Hasta. Okay. So much for this one. So since the FGLSS connection between PCPs and this one, for a good sort of 2.5 decades or so, there was a whole bunch of work trying to understand which problems you can solve, for which can you find tight hardness of approximations, and for a whole class of problems like max restat, max clique, all of them we found out exactly. Up to a point we could solve them. We had easy approximation algorithms for them, and just beyond that point, this theory of PCPs was sufficient to prove that it is NP hard to get any better approximation. So max clique, max 3 sat, max 3 lin, all of them fall into this one. Coming to Varun's question, one of the problems is clique. One of the problems is coloring. You're given a 3 colorable graph, you want to color it with as few colors as possible. This was one of the problems which we do not yet know how to solve. There are a few others. For example, vertex cover. Vertex cover, we know there's a 2 approximation. There's a half approximation algorithm. Can we do anything better than half? What we now know is we can't do anything better than 1 by square root 2, which is not as good as half. It's closer to 1 than 1 by 2. So we know how to do 1 by square root 2. You could ask, just like max clique, you could ask max cut. What's the best you can do for max cut? Max cut, we have seen the approximation algorithm is complicated. It's not as simple as for max 3 sat or clique or something. It was this Gomans-Williamson algorithm, if some of you have seen. It gave you some Gomans-Williamson constant. We don't yet know that that is the best algorithm that you can do. That is, anything better than that is NP hardness. We did not know how to do this. And all of this relates to the fact that many of these problems, what we care about is the PCP theorem that we proved is not strong enough to prove these results. And what Cote observed a few years later was he observed sort of he conjectured, Cote's conjecture is sort of a PCP theorem on steroids. So what did he say? He said there's a PCP theorem in which the number of queries is 2. It's not an arbitrary PCP theorem. You can show the PCP theorem in which the number of queries is 2. The predicate is a very special predicate. It's not an arbitrary. Right now, the PCP theorem allowed for an arbitrary predicate. It's a very special predicate. It's a predicate which was what I call a unique predicate, in the sense that it's making 2 queries. The moment you get one query, you know what is the answer to the other query that will satisfy the predicate. That is, moment you see one query, the answer to the other, the predicate is something of the form like the queries of the form like ax plus by equals c. So the moment you know x, you know what is the y that will satisfy the predicate, even before reading the thing. So these are what are called unique predicates. Suppose the predicate had this other feature, and furthermore, the completeness was 1 minus epsilon. You could make the completeness as close to 1 as possible, and soundness delta as close to 0 as possible for all delta and epsilon. If you had such a PCP theorem on steroids, then if this was your starting point, then you could prove that this is what is called the unique game conjecture of Cote. That such a PCP theorem exists. What Cote and several others observed, Cote, Regev, Cote, Kindler, KKMO, Mossel. Oh no, I run into trouble now. Oleskiewicz. Okay. They showed that, what did they show? Vertex cover, it's, let me call it UG hard instead of calling it NP hard, because it's a conditional result. Even the NP hard is conditional, but there's conditional on NP not equal to P. There's a condition based on this conjecture. It's UG hard to approximate better than half. Max cut is UG hard to approximate better than the Gomans-Williamson constant. So these are sort of known. So it is, if you assume this PCP theorem on steroids, then you do get these other algorithms also happen to be response. So there's been a lot of work trying to prove that the PCP theorem, this PCP theorem is actually true. And last year we almost came close to this, in which a couple of years ago, not last year, 2019 or 2018, 2018 possibly. So we got the queries, we got the completeness, we got the soundness. What we got was a predicate was not unique. It was something called very close to unique. It was what is called a 2-to-2 predicate. If that was a predicate, we were able to do this. So that also seems like a PCP theorem on steroids, but we were able to prove that. And yeah, so it's still the verdict is open whether the unique games conjecture is true or not. If it was true, it will imply a whole bunch of things. By the way, it still will not imply Varun's original question. We still won't know. We still won't know. We still won't know the hardness of 3 coloring. How many colors? That seems to require a completely new technique, and we don't know how to do this. So I'll stop with this.
So this thing that you mentioned that last year, there's like better PCP theorem, but not close to this. So
Yeah.
does that give you better inapproximability results for VC, max cut, and so on?
Which one? Yeah. So the vertex cover, the 1/√2, which I mentioned, comes from that.
Oh, okay.
The 1/√2 comes from that. The one prior to that result, we didn't have 1/√2. We had like something like that's a result due to Irid Dinur and Moli Safra from the early 2000s, which gave you, I think, 1/1.136, which is worse than √2 comes from this.
So could you just go back to the unique games conjecture?
Yeah.
So what this states is like for every L in NP, if you have a reduction to this PCP.
For every L or basically SAT.
Okay.
But it basically says SAT has such a PCP, a polynomial time, a restricted time verifier that tosses only random logarithmically random coins, but has the following feature. The number of queries is 2. The predicate is, by the way, it's not a Boolean alphabet. It's not, I should say it's not a Boolean alphabet. So let's state that the alphabet. So that's a relaxation. The alphabet need not be Boolean. In fact, it will not be Boolean. Not necessarily Boolean. So he says that if there is such a
so how do you write this promise language for 3 coloring?
Oh, the promise coloring for 3 coloring will be this. So if you're working with 3 color, the corresponding gap problem, the gap version. In fact, it's this one. It is the yes case will be G such that G is 3 colorable. A no case is G requires, so let's say N to be any, so M colors. That's a gap. If M was 4, this is a language. This is a gap.
What's the alpha here?
The alpha is 3 by M. M by 3 is the alpha.
Yeah.
And you can actually get even a smaller no prime, which is a subset of this, which says that usually what is proven is this one, that the alpha of G is less than or equal to 1 by M times the vertex set of G. That's a even small, that's a subclass of no. If the independent set is of size 1 by M, that shows that the number of colors has to be at least M. Fractional independent set is 1 by M. And usually we can, even with this yes, no, people manage to show some sort of, this is the gap version that is worked with for 3 coloring. Okay.
Yeah.
Okay.
So Prahladh, so suppose you're given a graph where you're promised that there is a clique of more or less linear size. Let's say, I don't know, some n by a million or something. There is a clique of that much size. But suppose your goal was to find the largest possible clique in this graph. I mean, that you can efficiently.
Yeah.
What is the best that we know? So the hardness result basically says you can't even get close to n to the delta. Right?
Yes. But not on these instances, not the.
Sorry, no. I'm just on an arbitrary instance. Suppose I give you an instance where I promise to you that the graph has a clique of size n over a million. And now I ask, what is the largest clique you can find in the graph? So Harstad's result basically says that you can't even find a clique of size n to the delta. Right. But what's the largest you can find? I mean, like in polynomial time. Like, for example, do we know of an algorithm that can find, say, a polylog sized clique?
Polylog. So the algorithms I know run in polylog, give you a polylog size clique. I don't know. Polylog is trivial basically. Log is trivial because you can, or even is log
Even
trivial?
that I don't know. I don't know anything more than constant actually.
No, polylog might be trivial because you just go over all. No, but you do not. You can't guarantee that there is one. No, you just go over all log n size sets.
But that is n to the log n many of them, right? So I don't know even how to do better than constant.
Actually,
So I was wondering.
no. So approximation wise, I don't know how to do. I don't know how to do anything better than constant. I don't know if these sort of lesser hierarchies give you anything for this.
Okay.
Yeah.
How does Harstad's result state that you can't go above n to the delta?
Because here is an example where the
Just
size
go
of
to
the largest
statement
clique.
once.
Prahladh, can you scroll up to Harstad's result? Yeah. So it says that, you know, like suppose here is a graph. I give you a graph where you know that the largest clique is of size, let's say n by a million. So Harstad's result says it is hard for you to even get a 1 over n minus epsilon approximation for this. Which means, like, basically, like, you can't even convince yourself that there is a clique of size n to the delta in this graph, where delta is basically playing the role of, I mean, or n to the epsilon in this graph. Yeah.
Yeah.
In the what did we know about like these problems like max 3 sat and stuff, that if you have okay, we have this PCP and that gives you this inapproximability, and I mean okay, the question that I want to really ask is, we know that if you have this PCP and steroids, then you can show better inapproximability for some more problems. But is that, do you need as strong a PCP as that, or is there some?
No, for max 3 set and all, you don't need it. Max 3 set, this is another result of Harstad, which for max 3 set, you don't need the steroid result. Max 3 set, this is a Harstad, that it is for all epsilon in 0, 1, NP hard to approximate max 3 set. So 7 by 8 is easy. So 7 by 8 plus epsilon. Anything better than 7 by 8. For this doesn't require the PCP theorem, just the usual PCP theorem which we know how to prove. From that you can prove this.
Prahladh, no, this question that RP was asking about having a clique of size n to the million.
So actually, I'm not sure that Harstad's theorem proves that.
Yeah, because you need to know where the yes cases go to.
Yeah. So Harstad's theorem won't imply this one. You have to show that the theorem continues to hold good even when the yes cases are chosen from this set.
Oh, I see. Okay. I see your point.
But by the way, Harstad theorem does prove that, but not the way I stated it.
Yeah. Okay.
Yeah. By the way, even this theorem, Harstad actually proves NP hard to approximate max 3 even when the input instance is perfectly satisfied. See, even when I tell you the satisfying instant is perfectly satisfiable, for you to find out better than a 7 by 8 is easy. Question is, can you do 7 by 8 plus epsilon? Yeah. And Harstad in that one paper of his proves a whole bunch of other papers. A few other problems he manages to show that they're all have the tight approximate results.
So this is something like I think I asked you before. Maybe I can ask after the stream ends. So why is it that for proving inapproximability of so many problems we need to work so hard as compared to like I mean just from the fact that they are all going to reduce to SAT, because in the clique case also eventually you rely on the car production and then you say something about its inapproximability.
Yes.
But like different problems target different parameters of the PCP for inapproximability results.
Yes.
But is there no unifying way of like saying, or is it just problem by problem basis that you have to?
So there is a unifying way. This is what Raghavendra tries to do in this one. What Raghavendra says is for each of these problems, we can come up with a okay. I'm going to say several things that possibly don't make sense, but so for each of these problems, let's work just with max CSP problems. I'm not so clique and max sat are different problems. Let's take max sat, max cut, max lin. These are all the same kind of problems. You're given a bunch of constraints and you have to find an assignment that satisfies the most number of constraints. These all problems fall into this bucket of problems. Vertex cover, clique, coloring are different problems. But let's look at max CSP problems. For all of them, there's a very natural SDP that one can write. A semi-definite program that optimizes this. We can write a semi-definite program and we can ask what is the integrality gap of this SDP. What does that mean? SDP is a relaxation. So actually what we want to find is an integer solution, whereas the SDP finds a solution, some vector solution. And integrality gap is the worst ratio between these two. So for each of these problems, there's a concept called the integrality gap. Now, what you can show is there is a single theorem, Raghavendra, which shows that if you believe the PCP theorem on steroids, you can show that that integrality gap is the best to obtain. You can't do anything better than that. And it's also easy to see how you can round that algorithm and you can achieve all the way up to the integrality gap. So it's sort of one sense a unifying theorem which puts all of these things. It takes in all the things that we have learned over the years. Raghavendra puts them together, at least for max CSP problems, and shows that for each of these problems, there's a natural SDP. That SDP defines the approximation ratio, and you can in one single shot show that you can't do anything better than that approximation ratio given by this integrality gap. So at least for max CSPs, this thing was done by Raghavendra.
Okay.
For other problems, I do not know. For max CSP, Raghavendra does get it. But it's not in some sense a unifying thing. He takes it involves everything that has been done. It's not a case-by-case proof, but it involves all the techniques that were used along the way.
Okay.
And possibly more. Yeah.
Also, one thing that suppose you have an approximation algorithm to some NP-hard problem, say it was some 1 over delta. Okay.
Yeah.
Now somebody gives a better approximation algorithm, then all the other approximation algorithms that we know about, their constants also change, right? Or
if you had an approximation, if you had an approximation preserving reduction between the two.
No, you can just do this normal car production, and then you can run the approximation algorithm, and then you can say that
you need to show that the car production preserves the approximation. You need to do whatever the FGLSS did observe, that if you had a gap before, you have a gap afterwards.
Oh, so normal reductions don't work.
No, it so happens all the car productions happen to be gap, but you need to make this observation. You need to do whatever FGLSS did. You need to go and observe. By the way, it's true for most of them, not for vertex cover. And vertex cover, we needed to do lots more hard work to do it. Yeah. Any other questions? Yeah. So then we will stop this, and this will end the module on PCPs. We will go to talking about. So for everything, we'll talk about a concrete lower bound in the next lecture. So we will talk about, I think, if you want to compute, how hard is parity to compute? And we'll show that if you restrict a model sufficiently small, then even parity becomes hard to compute. Parity, majority, we'll see.
Prahladh, for this 3 coloring problem, we know, right? It is hard with 5 or 6 or some constant number of colors, or even that is not.
So I think it's known only up to 7 or 8. I do not know NP hardness if it's known for more than that.
And that is also a proof in the same, along the same lines, that is constructing a different PCP or something.
No, the original proof was using PCPs, but now we know a non-PCP proof of that.
Okay.